Okay, we're starting the algebra textbook. Specifically, we're going to start the pre-algebra chapter, chapter R. In this video, we're going to start the opening section, which is on sets and the real number line. So one of the things that we're talking about in this section is the set of all real numbers, the real number line, and we want to analyze the set of all real numbers. What does that mean? How do you categorize different numbers within the set of all real numbers? Okay, but I think it's going to be very helpful for you if at the very beginning, at the very start of this algebra course, I go ahead and tell you about imaginary numbers or complex numbers. Just tell you what they are. Okay, and so that's what we're going to do here in this video. However, okay, what I want you to do, though, is do not get bogged down at all by what the meaning is of what I'm telling you here. Like, what exactly is a complex number? What does this mean? What is an imaginary number? Don't worry about that. We'll get into that later in chapter 1. All I'm trying to do here is make you aware that they exist. And not just that they exist, but how they're kind of the basics of how they're related to real numbers. So just focus on that. Do not get bogged down with what all this means. Okay, we'll get into that later. You just need to know that they exist, and I'm going to show you how they're related to real numbers. Okay, and then as we go through this section and as we go through the upcoming sections in pre-algebra, we'll be able to, as we look at different topics, we'll be able to kind of think about, okay, how would this kind of come into play with these complex or imaginary numbers? We'll be able to kind of think about that a little bit, which is going to be very helpful, as opposed to just, you've never heard of imaginary numbers at all, and it just gets thrown in at some point down the line. I think that can be very confusing. So, okay, up to this point, and everything you've done in math up to this point, we've been dealing strictly with real numbers. So, that's like any state a number right now. State any number that you've ever dealt with in your entire life. 5, 4, -3, 6.2, 0. Just any number that you've ever heard of, that's going to be a real number. Okay? Now, a useful way that we can kind of graphically represent this group of all real numbers is with a line. So you can draw a line, you can make a line in any orientation that you want. So we could do this graphical representation of this group of all real numbers with a line in any orientation. However, kind of the standard way to do this is to use a horizontal line. So we can it's a very useful graphical representation for this set or group of what we call real numbers. We can think about as on the real number line. Okay, and so we do. Okay, and then we give this a symbol here. This is the set of all real numbers. And this works because we know a line extends infinitely in both of its respective directions. And we know there's like an infinite, you could have 100 trillion billion, right? There's infinite numbers that go in the negative and positive directions. But even like between just 0 and 1, for example, there's an infinite number of values. So like you could have 0.38542, a trillion zeros, 83, etc., right? So this is a really good graphical representation of this group of all real numbers. It's like anytime you have a number that you're dealing with, you could come to this line here and pick one of these points and pick out a number to use, right? All of the numbers that exist in mathematics up to this point are on this line here. Okay. Now, what we're going to learn in chapter 1 is that we're actually going to extend all of the different numbers that we can choose from past just this line here. Okay, so I'm going to erase this R here because now we're going to look at this set of an extension of real numbers called complex numbers. Okay, And so, but I'm going to leave, but if you notice, though, I'm leaving this real number line here. So a part of this new set of numbers is going to include the numbers that we already have. But what we do is we're going to add another axis here. Okay, and now what we have is we've gone from, instead of just a line, now we can think about, we can pick any, first we could pick any number from a line. Now we can pick any number from a plane. Okay, and we call this the complex plane. It's like with this C here. Okay, so, but if you notice, though, we could still just, if we just stayed on this like horizontal axis, then we can still just pick out a real number like before. No problem. But now we have a freedom to move off of this axis here. But you're not supposed to put, like, I'm not supposed to put an R here like that, because it's not, it's technically this, we have this entire group now. This just means you have just this like group of just the real numbers. Now we have this new group of all of these numbers. Okay, and so what this axis is the, so it's still 1, 2, 3, but this is called, so this is called the real axis. This is called the imaginary axis. And each, when you go, okay, so you can now, again, you can pick any point in this plane now. Before you could kind of pick, to get a number, you could pick any number along this line. You can still do that if you want, but now you can pick any point within this plane is going to represent a number. So we've got a lot more numbers to choose from. Okay, and the idea is if you pick a point in the plane, okay, if we picked this point here, okay, this number, what is this number? This number is going to be, so we go 1 along the real axis, and we go 3 along what's called the imaginary axis. This is an imaginary number, and we multiply that 3 times I, which is, this is like the imaginary number I. Okay, now again, you might be thinking, well, what does this mean? Don't worry about it. Okay, but now this is a number, right? We can't combine these anymore. You know, before, if we had 1 plus 3, well, we could add 1 and 3 and get 4. But as this sits here, it's like these aren't like terms. We can't combine these anymore. This can't be simplified anymore. So this is it. This is a number. We call this a complex number, right? It's got, and you might hear imaginary numbers. That's just like, this is like an imaginary number. This is without the real part here. If you're on this axis and you're staying on this axis, you have a real number. If you're staying on this axis, you've got like an imaginary number. But if you're anywhere else off those axes, you've got a complex number. But technically, if you're considering all these numbers as complex numbers, even if you're just on the x-axis, you still have a complex number, right? This is just 0. Same here. If you're on this axis, you still have a complex number. It's just that in that case, this is 0, right? So, yeah, if you have picked this number over here, then okay, I have another number that is minus 3 minus 2i. There's another number. Okay, and so that's it. That's it. Going forward, we just want to keep in the back of our minds that when it comes to choosing a number, we technically have the option of picking any number from an entire plane like this, called the complex plane, which included within the complex plane is the original set of just all real numbers that we learned growing up. But now there's even more numbers. Now, if you get into higher levels of math, like PhD math, there's actually, I think, a couple of more categories of numbers: quaternions, octonions. But I'm not even sure if those are technically called numbers. But we're not going to be going there in this course and really on this channel. That's more for math majors. We just want to always have in the back of our minds that the array of numbers that we have to choose from are in a plane like this, called the complex plane. Okay, so let's just, don't worry about what this means. Don't be scratching your head and thinking, what does this mean? Don't worry about it, right? I, an imaginary number, what in the world is that? Don't worry about it. Just be aware. We just want to, as we go through this chapter, we just want to be aware that these additional numbers do exist. Even though that for all the problems that we're going to work in this section, we're going to be staying on this horizontal axis. We're never going to come off of it. You know, a lot of problems that you work in math for non-math majors, you just stay on this horizontal axis and don't move away from it. Okay, and so great. Now that you know about the existence of these imaginary or complex numbers, as we go through this chapter and even this textbook, we'll be able to at least think about what certain concepts that we're learning mean in terms of complex numbers. So, for example, we're going to learn about the inequality symbols, greater than, less than, etc. So, you know, we're thinking about on the real number line, you have one number is greater than or less than another number. Well, what would that mean in terms of if you're comparing two complex numbers, one being greater than or less than? Now, this isn't a full course on complex numbers. We're not going to be going too deep into this at all, but we can at least think about the idea of that's something that we would need to learn about complex numbers. Well, what's the kind of the parallel to greater than or less than in terms of complex numbers versus just the comparisons of real numbers? Okay, so with that, let's get started with this section here. And I'm not sure we'll be able to get through this entire section in this video. I might split this up into two videos. But okay, identify subsets of the set of real numbers. All right. A hybrid vehicle gets 48 miles per gallon in city driving and 52 miles per gallon on the highway. The formula A is equal to 1 over 48C plus 1 over 52H gives the amount of gas A in gallons for C miles of city driving and H miles of highway driving. In the formula, A, C, and H are called variables, and these represent values that are subject to change. The values 1 over 48 and 1 over 52 are called constants because their values do not change in the formula. Okay, so a vehicle gets 48 miles per gallon in city driving and 52 miles per gallon on the highway. So what they're saying here is that C would be the number of miles driven in the city, and H the number of miles driven on the highway. And so if you input C and H here, then you can get the amount of gas burned for the total miles driven on in the city and on the highway. Okay, and we call C, H, and A, these are variables because they're subject to change is what it says here. For different scenarios, you can input different amounts of miles driven in the city and on the highway, and you could have different amounts of gas burned depending on the circumstance. However, since we're talking about the same hybrid vehicle, then we look at the 1 over 48 and the 1 over 52, the miles per gallon in the city and the highway, as constants because they don't change. Okay? Now, if we think about this from the perspective of complex or imaginary numbers, then, you know, we kind of operate with I like it's a variable in the sense of how we, you know, when we have the number pi, we can kind of have, you know, 3 plus 2 pi. We can't combine these because they're not like terms in the same way we can't combine these because they're not like terms. However, we would consider I to be a constant because I is just a number in the same way pi would be considered just a constant. And another way of looking at a variable, when they say it's subject to change, that's one way of looking at it, that it's subject to change. But another way of looking at a variable is that it's a placeholder for potentially any number. Like you can apply restrictions to a variable. I could say x where x is greater than 0. So that would mean this would imply any real number that's greater than 0 is what x could be, right? But I could, you know, most of the time with the problems we're going to work when we have variables, we'll be assuming that they only represent some real number. But we could just as easily say that, look, x could be a real number or a complex number. This could be a placeholder for really any number. Okay? So, yeah, if you have They give an example. If you drove 36 miles in the city and 91 miles on the highway with this vehicle, then you burned 2.5 gallons of gas. All right, the numbers used in day-to-day life, such as those used to determine fuel consumption, come from the set of real numbers, denoted by this symbol R here. So yeah, you can think about the numbers on the number line. With this symbol R here. Okay, but now they use this term set, this set of real numbers. What is a set? A set is a collection of items called elements. So yeah, a set is just you're putting something into a group. But they're saying items. They're not saying numbers. Like here we have the set of all real numbers, because in math you can have sets of things that aren't numbers as well. Like in geometry, you could have the set of all circles, the set of all, so it's not just numbers. So they make it more abstract and call these, a set is a collection of items called the elements of the set. So the set of real numbers is represented with a symbol like this. And it's all the numbers on the number line. Now, when you draw the complex plane, even though it's true that, yes, this, like the set of all real numbers is kind of included in the complex plane, you don't put this symbol because that's implying that this is the set of all real numbers. No, this is the set of all complex numbers. So you just use this to represent the real. Okay, so like if you're going to say the set of real numbers, then you've boxed out everything but the real numbers. So you don't put this. Okay, so yeah, a set is just it's a term to represent a collection of elements. Elements could be, most of the time in this course, we're going to be talking about a collection of elements that are they're a collection of numbers, right? So the elements will be numbers, but they don't have to be. In geometry, we use the term set to represent sets of different figures, sets of triangles, subsets of triangles, right? So what would a subset be? It would be like if you had the set of all real numbers, okay, but if we're just including the numbers that are greater than 0, then that would be a subset of the real numbers, right? You could think about the set of all complex numbers. A subset of that would be the set of all real numbers, because we know that the real number line is contained entirely within the complex plane. Okay. Now, let's see. So we use the braces. These braces here are used to enclose the elements of a set. So yeah, you can, it doesn't have to be like the set of all real numbers is an infinite number of items or elements in the set, right? But you could have a set of 4 items, the set of the numbers 2, 1, -3, and 5. That's a set there. You can, a set is anything you want, absolutely anything you want. It's just something you're you're putting a box around and saying, okay, here's a set. All right. Now, note that a set that contains no elements is called the empty set or the null set. So if you have an empty set, that's called you call it an empty set or a null set, and you can denote that like this or like this. Okay. Now, when referring to individual elements of a set, the symbol, this kind of E here, means is an element of. And this symbol with the E with a cross through it means it's not an element of. So, for example, we could say that if we could take any set that we want and give it a variable name. So I could say this is set S, or let me say, this is set P. Okay, I could call that set P. And then I could say 5 is an element of P. Or I could say -7 is not an element of P. You see? Or when it comes to real numbers and imaginary numbers, I could say 2i is not an element of the set of all real numbers. You see? Okay. Now let's see. They've got that's what they do here. 5 is an element of this set. 6 is an element of this set. Okay, a set can be defined in several ways. Listing the elements in a set within braces is called the roster method. So this is the roster method. you listed it within, you just it's like a roster. You listed all that. That's what they're saying. It's like a roster would be, you actually list them all out like this. But if you have a set with an infinite number of items in it, you can't do that. Like the set of all real numbers. Using the roster method, the set of even numbers between 0 and 10 is represented by 2, 4, 6, 8 like this. Another method to define this set is by using set builder notation. This uses a description of the elements of the set. For example, okay, yeah, so if you can't use the roster method for whatever reason, you can use set builder notation, where you say, so you can write a description of the elements of the set. So the set of all is, you open with a bracket, that's the set of all. Well, it's more of this curly, the set of all x such that x is an even number between 0 and 10. You write it all out, and then you close it with, you close the brackets. I could also, to describe the real numbers, I could say something like the set of all x such that x is any number on the number line, right? I'm calling that the set of all real numbers, where the context is of what we would consider when we were in more elementary math courses, what we called the number line, right? Just learning basic arithmetic, what we looked at as the number line, the set of all numbers on the number line is the set of real numbers. Okay? Now, but there's also subsets, right? And I think it's pretty clear what a subset is. It's just a matter of context. It's just a set that's completely contained within another set. You could call it a subset. Like I could call this I just called this a set, the set P, but in another context, I could call this a subset in the sense that P is a subset of the real numbers, right? So it's just a term you can use to indicate that that a certain set you're referring to is completely contained within another set. Okay, now, but there's when it comes to the set of real numbers, there's ways we break down the real numbers into different subsets. Okay, so this set of all real numbers on the number line, okay, we categorize these numbers into different subsets. Okay, and here they are. They're the natural numbers, the whole numbers, the integers, the rational numbers, and the irrational numbers. And these are the symbols for these sets, right? That's the natural numbers, the rational numbers, etc. Okay, so the natural numbers are just going to be the counting numbers, not including 0. You could kind of think about this as what the cavemen would have, the only numbers they wouldn't even know what 0 is. 0 would be confusing to them. So 1, 2, 3, 4, 5. The counting numbers, it's not even including negative numbers. A caveman would be confused by a negative number as well. So the natural numbers, the counting numbers greater than 0. The whole numbers are just it's the natural numbers, but including 0. And so what you can think about there, though, is that the natural numbers are a subset of the whole numbers, right? Because every single natural number is a part of the set of whole numbers, all right? Next, you have the integers, which include, it's all of the whole numbers, but now we include negatives. It's counting numbers that include 0 and negatives. -1, -2, -3. Okay, but what you can see there is that the whole numbers are a subset of the integers, but then as a result of that, the natural numbers are a subset of the integers as well. Okay, next we've got the rational numbers. The rational numbers, so okay, what's a rational number? A rational number can be expressed as a ratio of integers, but where the denominator is not 0. So if you can express any number that you are able to express as a ratio of 2 integers, and what is an integer? This is an integer. These counting numbers, including 0 and negative numbers, if you can express it as a ratio of integers, that's a rational number. And what you can think about is from a decimal standpoint, if you've got any decimal that is or that terminate, if you have any decimal that terminates at some point, then you can represent that's a rational number. Because you can take I could take point, if it stops here, 0.321, I can write that as 321 over 1,000 and then just reduce that down. And then furthermore, though, if you have any repeating decimal, but it repeats in a pattern, like 0.3, it goes on infinitely, right? Like 0.3, this is just 0.3 repeating infinitely. That's also a rational number. We can represent any repeating decimal. So yeah, all terminating and repeating decimals are rational numbers. So the 0.71 terminates, 0.6 repeats, any kind of repeating pattern of a decimal that repeats to infinity, you can represent that as a ratio of integers. And so it's a rational number. Okay, but now you can think about, though, integers are rational numbers. I can represent any integer like this as a ratio of two integers. So all integers are rational numbers. So integers are subsets of rational numbers, and therefore so are whole numbers, and so are natural numbers, or subsets of rational numbers. Okay, so if now we've categorized all of the real numbers except for there's one more category that we're missing. Okay, and that's going to be the irrational numbers. So if you think about it, within rational numbers and integers and whole numbers and natural numbers, we couldn't include it within those pi or e or the square root of 2. And the reason is because these cannot be represented as a ratio of integers. And the way you think about what that means is that they're decimals that don't have any pattern. They're these infinite decimals that don't have a pattern, a specific pattern you can identify. Okay, so irrational numbers are real numbers that cannot be expressed as a ratio of integers. The decimal form of an irrational number is non-terminating and non-repeating. Examples, pi and root 2. Now, but these irrational numbers aren't going to be any kind of subset or rational numbers aren't going to be a subset of irrational numbers like we were seeing before. Kind of every single additional category here was a subset of the following category. That doesn't happen here. Irrational numbers are going to be in their own separate group compared to the natural, the whole, the integers, and the rational numbers. And so we can here they give a summary of of all the categories that we just broke the real numbers down into. Okay, so all real numbers here, you could break it down this way. You've got irrational numbers in their own group separately. They're a subset of the real numbers, obviously. But then from there, you've got all of the rational numbers here, and then subsets of those, you have the integers, the whole numbers, and the natural numbers. This fully categorizes all real numbers. Okay? And so just to make this clear, what we just did was, if we look at the complex plane, okay, we don't want to put this symbol here. This is not the set of all real numbers. This is the set of all complex numbers, but this is the real axis, and this is the imaginary axis. This still is, this is all the real numbers here in this horizontal axis. This is what we just broke down into the different categories. The entire x-axis here in the complex plane is what we just categorized. Okay, so in this example here, identifying elements of a set, they give the set A with these 1, 2, 3, 4, 5, 6, 7, 8 elements, these 8 real numbers here, and then they ask you to identify which are a part of the set of natural numbers, whole numbers, etc. So it's pretty straightforward. Okay. Now, inequality symbols and interval notation. Okay, so yeah, as I've mentioned, this course isn't for math majors. This is really more designed for non-math majors. And so, I think it's important for you to understand what a set is. We're going to be using the term set a lot in this entire course, but having to precisely use interval notation and whatnot, we're not going to go too deep into this here, okay? But just to give you a sense of what they're talking about here, that what they're referring to is that So we haven't been, obviously we haven't been introduced in the textbook to imaginary or complex numbers. So they're referring to, it's implied that we're referring to the set of all real numbers. Okay. And what we do is we can use inequality symbols as a way to compare two real numbers. Okay. We can specify, we could also use an equal symbol. We could say that. So if we've got two numbers on the real number line, maybe this number and this number, this is A and B, okay, maybe they're equal. That would mean they're the same number, right? Maybe they're equal. And so graphically they would be on top of one another on the real number line. But we can also, if they're not equal, there's ways we can compare them. We can say that that one is greater than the other. In this case, that would be true. B would be greater than A, and we write it this way. Or we could say, A is less than B. Okay. Now, in terms of just to think about, in terms of complex numbers, well, I think we have a sense of what it would mean to have two complex numbers equal to each other. If they lie on top of one another, then they're equal. But what would it mean if how would we compare if, we can represent a complex number with the variable z? That's typically the variable we use to represent it. Okay, but how would z1 compare to z2? Could we say z1 is greater than z2? Well, no, we can't. That's something we'll have to learn in more advanced courses, but it's interesting to think about what would kind of a parallel be as far as this makes sense on the real number line, which one's greater than the other, right? It's just which one's more to the right versus to the left. But it's going to be interesting to think about how we'll compare complex numbers in that sense of what would be like the parallel to greater than and less than in terms of complex numbers. Okay, so yeah, here's the inequality symbols. We've got, so A is less than B, or A is greater than B, okay? But you can also say, you can use this, less than or equal to, or greater than or equal to. Now, what does this mean? Well, you could say that if you've got two numbers on the real number line, A and B, well, you could say that A is less than or equal to B. Now, what would that mean? Well, in that case, you would kind of you might be looking at A more of like a variable. A is subject to change, right? But you're specifying that it's going to be some number that's less than or equal to B. And you could kind of look at that as a set, the set of all numbers that are less than or equal to B, which would be a subset of the real numbers. Okay. Now you also have A could be equal to B. A could be not equal to B. That's another way you could say that. You could describe the relationship between these two real numbers, and you could do that with complex numbers as well. That makes sense if they don't lie on top of one another. Okay, but again, what would this mean? I don't know. We have to talk about that another time. Okay, but then there's also A is approximately equal to B. So like minus 12.99 is approximately equal to minus 13. Like when you round, you're kind of making an approximation. All right, an interval on the real number line can be represented in set builder notation or in interval notation. Yeah, you can take any interval on the real number line and kind of represent it like it's a subset. It is a subset. And you can kind of specify it that way. You can say if you've got the real number line here, you can kind of specify this subset of all numbers that are less than or equal to 1. All real numbers that are less than or equal to 1, you could kind of, going into a problem or something, you could say, okay, this is what we're considering. Consider the set of all real numbers less than or equal to 1, which would be a subset of the real numbers. You could say that. Or a problem might tell you that, right? So like you can think about that as a set or a subset. So, okay. Now, I don't want to get into too much of the math notation here. Let's see. So they give some examples here of doing this. So in the set of all numbers that's greater than a, not greater than or equal to a, just greater than a, you could write it in set builder notation like this. The set of all x such that x is greater than a. You could put it graphically like this. So on the number line, you do, so if this is a, you put a open bracket here and kind of do that. Or you could do it in interval notation with a, like this, from a to infinity with the parentheses, not a bracket. But if you wanted to say greater than or equal to a, then you would do this, then you'd make this a bracket, or in the interval notation, you would do this. And if you have an infinity term, you put an arrow like that, and you put a you don't put a bracket with the infinity. And then you could do it's the same idea if you're like the set of all real numbers between a and b, but not including a and b. You see how they do that here? The set of all x such that a is less than x, which is less than b, so x is between a and b. They put the graph here with the parentheses, and then in interval notation, it's like this. So we'll use all this notation as we go through the course, and you'll get a feel for it. It's pretty straightforward. But just note that all of these are subsets of real numbers that you can put in their own box and put off to the side for analysis or for describing something. And yeah, here's like the set of all real numbers, right? So minus infinity to infinity. The set of all x such that x is a real number. Okay, now something else we can do with sets is we can perform operations to create new sets from previous sets. So the operations of union or intersection. So like, just think about it. We could take any of these sets here, or the set of all natural numbers, whatever, okay, and we can perform an operation of that set, or like any of these sets with another set and get a new set. So I could say the set of all natural numbers in union with the set of all whole numbers is going to create this new set I'll call S. Okay, and all this means is that it's just really straightforward. All union, it's either union or intersection are the two operations. And what it's saying is that, so if you have the union of two sets, we can just look here, all you're saying is everything in set A and everything in set B is the union of two sets. So you'd have if I did the set of natural numbers in union with the set of whole numbers in this new set, I'm just saying this new set contains everything in the natural numbers and everything in the whole numbers. Okay. However, note that you don't repeat elements twice. So if we come back, if we took the union of the natural numbers and the sets of natural numbers and whole numbers, it's not like we would have 2 1s and 2 2s. No. You just take everything in set 1 and everything in set 2, but remove the duplicates. So we just have pretty much what we would be doing is this is actually interesting because it would be, since the natural numbers are a subset of the whole numbers, then the union of those two sets would just be the set of whole numbers, right? Because, why is that? Because the natural numbers are a subset of the whole numbers. The only difference is the number 0 is a part of the whole numbers, but not a part of the natural numbers. So when you take the union of these two, which is all of this, but take out the duplicates, well, what do you have? What are we left with? I just shaded in the whole numbers. You see? So the set of natural numbers in union with the set of whole numbers would be just the set of whole numbers. Now, what about the intersection? It's interesting to actually do this in terms of the intersection. So the intersection of two sets is everything that's contained in both A and B. You see how it's like shown here, right? Well, what would that be if we had the intersection of the natural numbers and the whole number sets? Well, in that case, it's just going to be the natural numbers because there's no duplicates, right? So if the natural numbers are a subset of the whole numbers, but 0 is not included with the natural numbers, well, the only intersection is here. That's all the natural numbers. But you can see how there could be different cases where you have a portion of one set is just overlapping another portion of another set. When it comes to the categorizing of real numbers, it's kind of, it's either they're completely separate sets, like irrational numbers are completely over here compared to the rational numbers, and then all the other categories are all subsets of the rational numbers. So this is kind of a unique case here, but in a lot of cases, you could have sets that are overlapping. And so in that case, you have different meanings of union and intersection, etc.